Hello, and welcome to this sixth set of problems on complex numbers. In this video, we will solve problem number 51 to 60. So, as always, I'll say that when I'm stating the problem, you should pause the video and try to solve the problem yourself. If you cannot solve the problem yourself, only then look at the solution. With that, after saying that, I'll just get started. Problem 51 says that if mod of z plus 6 is equal to mod of 2z plus 3, then prove that mod of z is equal to 3. So we let z is equal to x plus iy. Then z plus 6 becomes x plus 6 plus iy. And this becomes 2x plus 3 plus 2iy. So we square both sides. We get left hand side as x plus 6 whole square plus y square is equal to 2x plus 3 whole square plus 4y square. Now it is straightforward to see that this will become x square plus 12x plus 36 plus y square, and right hand side will become 4x square plus 12x plus 9 plus 4y square. So this 12x will get cancelled. We bring x square and y square to right hand side. So we get 3x square plus 2y square, and we take 9 to that side. We get 36 minus 9, that is 27. This is 3y square, not 2y square. It's a typo. So now we see that x square plus y square is equal to 9. That means mod of z is equal to 3. Problem 52 says that if square root of a minus ib is equal to x minus iy, then prove that square root of a plus ib is equal to x plus iy. So we square the given expression or equality. We get a minus ib is equal to x square minus y square minus 2yxy. So we compare real and imaginary parts. We get a is equal to x square minus y square and b is equal to 2xy. Now a plus ib becomes x square minus y square plus 2ixy. So you can replace this minus with I square. You get x square plus I square y square plus 2ixy. Now this whole thing is square of x plus iy. So taking square root, we get a plus ib is equal to x plus iy. Problem 53 says that if xr is equal to cos pi by 2 to the power r plus I sin pi by 2 to the power r, then find the values of x1, x2, x3 up to infinity. So from the complex numbers, you know that it can be represented as e to the power I theta, that is cos theta plus I sin theta can be represented as e to the power I theta. So suppose there are many such complex numbers and the powers are theta 1, theta 2, theta 3 and so on, then the product will be e to the power I into theta 1 plus theta 2 plus theta 3 and so on. And thus we can say that this x1 into x2, the product on left hand side, will be equal to cos into pi by 2 plus pi by 2 square plus up to infinity, and I sin pi by 2 plus pi by 2 square up to infinity. Now in both of these terms inside parentheses, the first term is pi by 2 and common ratio is 1 by 2. You can clearly see that it's a geometric progression with common ratio 1 by 2. So we write cos pi by 2 into 1 by 1 minus 1 by 2. From geometric progression, if you recall, if the first term is a and common ratio is r, where mod of r is less than 1, then sum of infinite terms is a by 1 minus r. So that's what formula we have used. So now it simply becomes cos pi plus I sin pi, which is equal to minus 1. Problem 54 says that find the value of cos theta plus I sin theta to the power 4 by sin theta plus I cos theta to the power 2. So, this is 5, not 2. This is a typo. So we have cos theta plus I sin theta to the power 4 divided by sin theta plus I cos theta to the power 5. So we take I out from denominator. So we get 1 by 5 sin theta, 1 by I sin theta plus cos theta to the power 5. Now what we do is we can write 1 by I as minus I. So denominator becomes I into cos theta minus I sin theta to the power 5. Note that I to the power 5 is equal to I to the power 4 plus into I. So this becomes I because I to the power 4 is 1. So once we have this, we know that this is e to the power minus I theta. So we take out minus and we bring it in front of 5. It becomes minus 5. And the minus sign of I sin theta becomes plus sign. So now our final value will be 1 by I into cos theta plus I sin theta to the power 9, because 5 will go at the top and get added to 4. So 4 plus 5 is 9. So then you bring 9 inside and you get cos 9 theta plus I sin 9 theta. And then divide the whole thing by I, you get sin 9 theta minus I cos 9 theta. Problem 55 says that if z is equal to square root of 3 by 2 plus I by 2 to the power 5 plus square root of 3 by 2 minus I by 2 whole to the power 5, then find imaginary part of this complex number. So we can write root 3 by 2 as cos pi by 6 and 1 by 2 as sin pi by 6. So we get this whole to the power 5, and here the sign will be minus, and we get this whole to the power 5. Now we bring this inside, we get cos 5 pi by 6 plus I sin 5 pi by 6 plus cos 5 pi by 6 minus I sin 5 pi by 6. So the sign terms will get cancelled because of difference in signs, and this will become 2 cos 5 pi by 6, which is purely real, so imaginary part of z is 0. Problem 56 says that find the product of all values of cos pi by 3 plus I sin pi by 3 whole to the power 3 by 4. So in this case, we bring 3 down, so pi by 3 will get multiplied with 3, becomes cos pi, and this will become I sin pi whole to the power 1 by 4. Now the general value we have already studied will be cos 2n pi plus pi by 4 plus I sin 2n pi plus pi by 4. So we substitute n is equal to 0, 1, 2, 3, and the product would be this much. So in the first case, the argument would be pi. In the second case, it would be 3 pi. In the third term, it would be 5 pi. And in the fourth term, it is 7 pi. And then we substitute the values of those cosines and sines of angle, and we simplify. We finally get the value as 1. Problem 57 says that if z1 and z2 are two non-zero complex numbers such that mod of z1 plus z2 is equal to mod of z1 plus mod of z2, then find argument of z1 minus argument of z2. So in this case, it is convenient to use polar coordinates. So I have let z1 is equal to r1 cos x plus I sin x, and z2 is equal to r2 cos y plus I sin y. So mod of z1 plus z2, you square that, you will get r1 cos x plus r2 cos y. The real terms are together, whole square plus r1 sin x plus r2 sin y, the imaginary terms and square of that. And right hand side would be r1 plus r2, which is the modulus of z1 and z2 whole square. So we'll get r1 square plus r2 square is plus 2r1 r2. Now left hand side, r1 cos square x will get added with r1 sin square x, giving r1 square, which will get cancelled. Similarly, r2 cos square y and r2 sin square y, r2 square sin square y, both will get added and give r2 square, which will get cancelled from right hand side. So what will remain is 2r1 r2 cos x plus cos y from this term, and 2r1 r2 sin x sin y from here. So I have taken 2r1 r2 common, and this r1 r2, this is r1, not r2 r2. This is the typo. So this 2r1 r2 from here. So 2r1 r2 will get cancelled, and this is equal to cos x minus y is equal to 1. This clearly implies that x minus y is equal to 0. So argument of z1 minus argument of z2 is 0. Problem 58 says that if z is equal to 1 minus sin alpha plus I cos alpha, where alpha is in the set of 0 to pi by 2, then find the modulus and principal value of its argument. So again, it is convenient to express this as a polar complex number, that is r cos theta plus I sin theta. So r would be real term square and then imaginary term square, that is 1 minus sin alpha whole square plus cos square alpha. So this will give 1 minus 2 cos alpha plus sin square alpha plus cos square alpha. Sin square alpha and cos square alpha is equal to 1, which will get added to 1. It becomes 2 minus 2 sin alpha. Now we evaluate tan theta is equal to cos alpha by 1 minus sin alpha. Okay. Now cos alpha is 1 minus tan square alpha by 2 by 1 plus tan square alpha by 2. And sin alpha is 2 tan alpha by 1 plus tan square alpha by 2. So we have taken LCM here. We can write this is 1 plus tan square alpha by 2 minus 2 tan alpha by 2. And 1 plus tan square alpha by 2 in the denominator of both these terms I have cancelled. Now you can see that the denominator can be written as 1 minus tan alpha by 2 whole square. So I have cancelled 1 minus tan alpha by 2, and numerator is now 1 plus tan alpha by 2, and denominator is 1 minus tan alpha by 2. Now here you can write the 1 in numerator, this 1 in numerator as tan pi by 4. And with this tan alpha by 2, you can imagine that 1 is multiplied, that is tan pi by 4 into tan alpha by 2. So from trigonometry, you can write this as tan pi by 4 minus alpha by 2. So theta is equal to pi by 4 minus alpha by 2. Problem 59 says that find the value of the expression 1 plus sine pi by 8 plus I cos pi by 8 divided by 1 plus sine pi by 8 minus I cos pi by 8 whole to the power 8. So we let z is equal to the given complex number, and then we multiply with complex conjugate of denominator, we get this value. Now I'll try to explain that what happens after this. So this will give us 1 plus 2 sine pi by 8 plus sine square pi by 8, and I have taken the 1, and I have taken 1 minus cos square pi by 8 as sine square pi by 8. So that sine square pi by 8 will get added to sine square pi by 8 from this. So we get 2 sine pi by 8 plus 2 sine square pi by 8. And this part I have left as it is, after which we got after multiplying these two. Now this is equal to 2 plus 2 sine pi by 8, because sine square pi by 8 and cos square pi by 8 is 1. That will get added with 1 of this term. So it is 2 plus 2 sine pi by 8. Now you can see this will get cancelled with this. If you take sine pi by 8 common, so this real part is sine pi by 8, and here 1 plus sine pi by 8 will get cancelled here, but 2 and 2 will get cancelled here. So this will be cos pi by 8. So what we get is sine pi by 8 plus I cos pi by 8. This we can write as, after taking I common, cos pi by 8 minus I sine pi by 8. So z to the power 8 would be I to the power 8 cos pi minus I sin pi. Now I to the power 8 is multiple of 4. So this will be 1. Cos pi is minus 1 and I sin pi is 0. So z to the power 8 would be minus 1. Problem 60 says that if z to the power r is equal, zr is equal to cos 2r pi by 5 plus I sin 2r pi by 5, where r is equal to 0, 1, 2, 3, 4, then find z1, z2, z3, z4, z5. So we solve this. Okay, so one thing, I think I made a mistake here. So you can assume that r starts from 1 and goes up to 5. Okay, so this is basically my mistake. The original question is 0 to 4, but you can think it is 1 to 5. So like previous problem, I have written z1 to z5, it becomes cos of 2 pi by 5 plus 4 pi by 5 plus 6 pi by 5 and up to 10 pi by 5. And similarly for sine. Now you add these, because these are in arithmetic progression. So the value of sum would be n by 2 into first term plus last term. So n is 5, 5 by 2 into 2 plus 10, 12. So 12 when divided by 2 will be 6, and 6 into 5 is 30 pi by 5. So we have this 30 pi by 5, and we have the same value for sine. Now this is equal to cos 6 pi plus I sin 6 pi. Now these are multiples of 2 pi, so cos 6 pi would be 1 and I sin 6 pi would be 0. So the final value is 1. So with this we come to the end of 6th set of problem. If you have a question or comment, or you want to correct something, let me know in comments. Also, please subscribe to the channel and like the video so that it reaches to many more people, because that's how YouTube algorithm works. And I'll see you in the next video with more problems on complex numbers. Thanks a lot for watching. Enjoy.